I think we'll go ahead and get rolling. So tonight is lecture 5, and we're going to go over the very first machine learning, the first machine learning model, the linear regression model. That's the main thing we're going to do tonight in a very exhaustive manner. Yeah, so first thing, a little bit of logistics. Talk about the IRIS homework, the very first one. We're going to go over what I've gotten from you guys on that. And then we're not going to talk about the neural network homework. Well, I'm going to review that homework again, with you guys, because I haven't gotten any submissions yet. And then I'm going to go over the rest of the linear algebra mathematics that we need for this. Then we're going to jump into linear regression. And I'm basically going to give you guys 2 different views of linear regression and how it works, the behind the scenes, 2 different views behind the scenes. And these are not the stock models that you get out of, out of scikit-learn, Keras, or R, the models that you just pull in. I'm going to show you stuff behind the scenes, how they come up with the models, how they come up with the parameters. So that's the goal tonight for going through. So we got a packed night tonight. All right, so some basic stuff on me. I'm just going to post this at the beginning of each of the lectures. Got my phone number here if you guys need to call me. If you need some help, stuck on something, if you need a boost on the neural network homework, or the IRIS homework, please reach out in any way that you feel fit. Yeah, so, and there's my GitHub, which we're going to be delving into that tonight. Just like last night. Okay, last week. All right, so I got 7 submissions for the homework. From the homework 4. So what we'll do is just kind of take a quick look at these. I'm very, very familiar with the initial, initial notebook that I put together. And then there's a bunch of stuff added, which I'm like just really very pleased with the stuff that I see. It's very good, especially for your first shot at some of this. So yeah, let's go ahead and just start taking a look at this. Okay, so I just brought the GitHub right in here, so should be able to just click on it. All right, so let's see, there's, okay, just gonna kind of go down this real quick. All right, I'm not sure what happened up here, descriptions, but yeah, then we pull in the data, set the data up, and do some stuff about showing how big the data is, which is nice. Train set, target set, very nice. And then show some of the data here. This is the first 5. That's what head gives you. And then some details about the data sets, and you transpose it, which is very nice because we only have 4 rows. It's a lot easier to look at it going across. So we have 112 rows for everything. This is, I believe I did this as well in mine, but this is nicer going across. Okay, so now the scatter plot, very nice scatter plots. So you're using the scatter matrix, which is you got to diagnose the KDE. So some of the stuff I'm not familiar with. You guys are, definitely, there on it. So I see you've got the clusters for each of these scatter plots. So that kind of shows, where these different the different classifications are. So that's very nice. Okay, and then looking at the data sets, okay, doing some distributions. So that's nice. More scatter plots. Actually, this is the okay, scatter matrix, but now looking at the distributions for each of the variables. That's nice. So good, some extra stuff added. Okay, then now we're going through each of the model types. And I'm not sure if I think I had a couple more in there, but so you're scoring all of them, giving the different scores, statistical scores, and actually no, just one score. You're scoring each of the models. That's it. So this gives you a very good idea of which is the best. And then a bar plot, bar chart showing it going across. So you can see which ones are the best, and then you pick the best and show a bunch of different, or this is just the learning rate. So, the more depth, the better your answer is, and this will become much more apparent later on when we go into random forest and decision trees in depth, what we mean by max depth. So max depth of 5 gives you the most accuracy. So you're showing that, doing the prediction, and you got your accuracy scores. So okay. Then we have a decision tree showing the final decision tree. That's very nice. Did a really good job here. And then show the feature importance. That's super important. So this shows the correlation, shows how important each one of your inputs is to that output. So we're seeing that petal length is the most correlated, as you get the most information out of that feature as far as which type this is. And the least would be the sepal width, probably because it's very small and not much variation in it. So graph that's nice, and that's it. This is great. Did a very good job. That was Tajuddin. Okay, so let's go on. Some of these will be going more quickly through. Okay, so on this one, okay, everything looks pretty standard up to now, but everything that I did. Box and whisker, his scatter plots. Okay, broke the data set out. Okay, spot check. Okay, all the standard ones. Make the predictions. Okay, then additional stuff. Okay, here's where there's additional stuff. Okay, so some more graphs, basically, some more charts showing the classifications in colors. That's very nice. Shows the histogram of these of the different values and which ones they are. So you can see that whichever one the blue is, which is Iris setosa, has the smallest sepal length. Because this one is a sepal length by sepal length. It's not a scatter plot; it's just a histogram. So it has the smallest sepal length, but then the Iris virginica has the biggest one. Whereas the sepal width is very wide for the Iris setosa. So just from these graphs, you can get very good information about these flowers. Okay, then you added the K-Mings clustering. Okay, so try to break this up by itself. So this is how, if you just had the data, could you break this up into several species? It did that. It found its own, a natural way that these flowers, you've got 3 different types of flowers. Don't know what kind they are. You're not looking at what type they are. You're only looking at the features of them. And it automatically breaks them up. So now what we're going to do, I'm assuming, is how close was that to the right answer? And it looks like 83% of the time, it was right. It broke it up into good, it was a good breakup. So took a look at it, you saw species 0 looks like Iris vertosa. Species 1 looks like Iris setosa. So that's kind of how this, how they did that. So, and then how accurate was that? 83%. So that's nice. Simple neural network. Okay, very good. A TensorFlow. Use a TensorFlow. So, yeah. So this is setting up the graphs. The graph moving from one to the next, and this is going to be much more complicated than I want to get into tonight. But this is very nice. It's much different, much simpler than, my deep down, this is how you do everything. You just basically do this reduced mean, you set up a gradient descent optimizer. You set up a cost, you set up an optimizer, and then you say minimize the cost based on the gradient descent, and it just runs. And okay, it's nice because you see how long it takes to run. Okay, that's nice. So, and then it's showing the accuracy as you train. Looks like it gets more accurate, and it maxes out on the accuracy. And it took 7.8 seconds. So yeah, that's very nice. I like it. Okay, that was Raphael. Okay, Mosun, let's look at yours. All right, so okay, everything to start with is the same as mine. Probably have the homework down at the bottom. Okay, you scaled the data set using standard scaler. So the data set originally was, like, different. Let's see if we have the values up here. The average was 5.8. The minimum was 4.3. The maximum was 7.9. Well, you sometimes can get better answers if you scale this down to between -1 and 1. So bring everything within its similar values. And this becomes really important if you have some values that are like $1,000, whereas other variables are like 1, 2, and 3, like count, something like that. So you want to bring everything to around the same values. So it looks like sepal length became, around -1. These must be the smaller ones. Sepal width, these are also pretty low. So these are just the first few of the data, pieces of the data. Okay, so you added that, and then you're doing the training. Okay, and training accuracy, comparison, and then some predictions. Okay, then, okay, random forest, was that one of the Yeah, that's one of the most accurate. So okay, so basically you just took everything to the looked at the accuracy of more of them. Um, how more or less accurate were some of these other ones. So that was good. Okay. All right, so I'm going to go over more of them later. Actually, let's do Peters, and then the rest of them I'm going to go over later if there's time at the end. Okay, so looking at Peters. Okay, so same. Okay, many more things are loaded in. Okay, so it looks like more model types like naive Bayes, ensemble neighbors. Okay. Okay, so we got the data set, showing the data set. Okay, breaking it down. There's 50 of each type. Okay, the statistical. Okay, this is all the stuff that I had. Okay, then doing scatter matrices. That's nice. And okay, now this is a different type of scatter plot. It's more okay. This is saying that for sepal length for Iris setosa, they're around here. Iris versatosa, they're here. Okay, so this is good. This is a different view, different way of looking at it. Okay, training set, test set. Okay, so this is different smaller validations basically. Okay. Okay, so different. Okay, so now lots of different hyperparameters for all these different models. That's awesome. Okay, so we have many different models here, and so we're going to go through and set the hyperparameters for each one of these models, and that's awesome. So when we go into each one of these models, we will look at all the hyperparameters. The first one, linear regression, there isn't much as far as hyperparameters go. But as we go into these other ones, there will be much more. Okay, so the K-folds. Okay, so help on that. So how to use it. Okay, so several. Okay, so now you're running all the models based on the hyperparameters that you set at first. Okay, so we got some these errors are okay. So these are just different warnings. Could be because of different versions. So okay, so we got accuracies like SVM sigmoid, pretty low accuracy. So that doesn't seem to be very good. Okay. So then we're plotting all the accuracies. So that one, this probably we need to split this out or flip it on its side so we can be able to read all the different types. Okay, so now looking at the confusion matrices on a few of them and looking at how accurate they are. So got the accuracy score on a bunch of them. Just used every model that you could find, and that's awesome. Okay. All right, so all right, let's move on. Okay, so that's the homework. Now, the next thing we're going to go through fairly quickly is the basis of basic linear algebra. We went through a couple things before, but it was pretty rushed. I'm going to go through more of it this time. And this should be basic review for most of you, but For some, this might be the first time you've seen it. So we'll go ahead and go through it. Okay, this first one, we're not going to go through that again. The structure is a scalar, vector, matrix, tensor. But so some basic mathematics. Okay, so some of the requirements. Okay, so for addition and subtraction, requirements are that your matrices have to be the same size. Matrix, vector, everything. The tensor, they all have to be the same exact dimensions, x by y. So when you add them, I mean, it's pretty simple. You just add each element by itself. So for matrix multiplication, okay, you have to match up the columns of the first one with the rows of the second multiplication. So when you do that, like what you end up with is you drop the middle, so you end up with a 2 by 1 matrix when you multiply these together. And what you do is you take this row times this column to get that value, and then this row times this column to get the bottom value. So basic operations. Okay, another one is to transpose a matrix. To transpose, you take everything and flip it around the axis, around the 1, 5, and 9. You leave that the same, but then you flip the 4 and the 2, flip the 7 and the 3, flip the 8 and the 6, and then here you're gonna your dimensions are gonna flip also if you flip everything. You're basically flipping the 1, 2 around the 1, 2, and 3, and the 8, 8, 6, and then the 7, 9, 1. Everything else is going to flip, and then you end up with instead of a 5 by 3 matrix, you end up with a 3 by 5. Okay, so that's pretty straightforward. Okay, now we're going to talk about the identity matrix, because the next thing we're going to do is invert. So the identity matrix is the matrix that if you multiply it by another matrix, you end up with the same matrix. It's like multiplying by 1. And it's pretty easy to prove that. If you take this row, multiply by this column, okay, the A12 and A13 drop out, you end up with A11 over here. Likewise for everything else. So, and it doesn't matter what side you put the identity matrix on, you can put it on the other side also. Now, that's if it's a matrix C that's like n by n, where the rows and columns are the same, then you can flip it. If you take a look at this multiplication, here I've got a 2 by 3 matrix. I'm going to multiply that by a 3 by 3. 2 by 3 times a 3 by 3 equals a 2 by 3. And it equals the same thing. And you can see here, taking this row by this column, gives me this one, this row by this column, give me this one, so forth and so on. Okay, so yeah, now you can't just flip this around though and put this one in front. You can't take a 3 by 3 and multiply by a 2 by 3. You'll have to change this to a 2 by 2 matrix, identity matrix for that to work. Any questions about that? That should be pretty straightforward. This should be review for most of you. Okay, so now we're going to talk about inverse. And what do I mean by inverse? It's the same as like 1 over. Okay, it's what you multiply by the matrix, your original matrix, to get 1 or your identity matrix. So what is it that you multiply? It's another matrix, and it is the inverse matrix. It isn't just like 1 over this, but you can think of it that way. So how do you how do you come up with the inverse matrix? There's a formula, and I'm showing the basics of that formula just applied to a 2x2, but this extends up to other ones. What we do is just use Python to do this inverse. But as you can see here, to do this one by hand, okay, you take your original matrix, A, B, C, D, all right, you flip the A and the D, so that becomes D and A, and then your other axis, you make negative. Okay, so that's the first thing you do. And then you take that and multiply by a scalar on the outside. And that's the scalar that you multiply by is, I wish I could get rid of this thing. It's just annoying me. Not sure how to do that though. Nope, don't know. Anyway, you multiply it by this this scalar, which is your I forget what you call it, AD time or minus BC. So once you do that, I think on the next one I have an example. No, I don't have an example. You end up with the inverse, such that when you multiply by your original matrix, ABCD, you get 1, 0, 0, 1. If there's any questions about this, please reach out. This is something very, very, very important, because this, if you got to understand, where this stuff comes from when you when you look at how these what the math is behind all of this stuff. It's not that complicated. We're not going into heavy mathematics here, but there is some basic stuff. Okay, okay, that's it for the mathematics part. All right, so I'm going to give you guys kind of a top-down view of the machine learning techniques, and this will help you understand, why I picked linear regression to start with. How do all of these work? So every machine learning is all about prediction. Okay, predicting something based on some data. Okay, now what is it that we're predicting will take our machine learning techniques and break it into two big types, classifications, I guess I could say. One of the two types would be a classification algorithm. The other one is a regression algorithm. If we are trying to divide our data up into different sets of data, different types, whether it's one is yes or no, or like 1, 2, 3, 4, or 3 different flower types, then we are going to use a classification algorithm. If we are trying to predict a continuous variable, a number, like predict a price, predict a distance, something like that, predict a count of things, if those counts are very, very large, then we're going to use a regression algorithm. And so the outputs will be just numeric, versus classification algorithms. Our outputs are a type of something. And if it's a 1, if the output becomes a 1, then the type is one type. If the output becomes a 0, the type is another type. It's not that type. Okay, got a question about inverse of a 3x3 matrix. Oh, that's a good question, and that you only asked that question to me, Srinivas, and Vas, you are also just messaging me, which that may be what your intention was, but yeah. So Srinivas, your question is how to inverse a 3x3 matrix. Can we have an inverse of an m by n matrix? Okay, you cannot take an inverse of any matrix. It has to have the same number of rows as columns. That's the only way you're going to end up with that identity matrix. And how to get it the 3x3? I don't want to go through that here, but yeah, that's a pretty. It's a long formula. It's very, very similar to what we did here. This is going to be more complicated. Your scalar multiplication and your rearrangement is going to be a little more complicated. Not much. It's a very good pattern. Oh, determinant. That's what that is. That's what the scalar is. So, so yeah, that's we can go into that, but it's a little bit beyond what I want to go through here. Okay, so anyway, so these different algorithms, we've divided up into two different types of machine learning techniques, and this is all the supervised techniques. We're not talking at all about unsupervised yet or semi-supervised. Right off the bat, we're just doing supervised. So different types of classification algorithms, the logistic regression, k-nearest neighbors, decision trees, naive Bayes, linear support, vector class, classification. Those are all classification algorithms. There's a few regression algorithms, which we're going to start with that tonight, linear regression. Logistic regression is going to be, I know it says regression there, but it is actually a classification. It's going to be the same as linear regression. We're going to do that first next week, and then we're going to do decision trees after that, because it won't be much beyond what we talk about tonight to do logistic regression. So regression trees is another random forest. Those are regression algorithms, and then support vector regression. The support vector classification is very similar to the regression. So there's a lot of parallels between these algorithms, and I'll give you a hint of where the parallels are tonight. Okay, so that's breaking this down. Our machine learning techniques, you guys are going to need to memorize this. You're going to need to understand it, and you will over time once you get familiar with each one of these algorithms, once you start using them. All we did last week with the iris, we did classifications. We didn't do regressions. Why? Because we were classifying. We had our our biologist hat on. We were classifying irises. So therefore, classification algorithm. Tonight, we're going to look at a simple one, which is like salary, versus years. That's what we're going to look at for regression. That's one of the things. Okay. So the way we're going to attack this, the linear regression, is first get an overall idea of what are we trying to do with linear regression. Then we're going to dig into. We're going to look at some data sets that we can use for this. A couple of them, and then we're going to hone in on just one. And then we're going to develop the methods, the models, using two different methodologies. One is the matrix solution, which is using some matrix mathematics, and then we're going to do gradient descent, which we did last week with neural networks. We're going to do it again this week. And then we're going to compare our linear regression model to neural networks, which is very, very, very simple. I mean, very, very similar. Okay, so what kind of problem do we apply linear regression to? It's a regressive problem, which means that it's not a classification. Here we're looking at, okay, as your years of experience go up, generally your salary goes up. So this isn't, what type of salary, what type of employee. This is, a dollar amount. And then generally it goes up as years of experience. This is taken from somewhere. Now, why would we use linear regression for this versus another technique? If we take a look here, it's a pretty straight line. So that would imply that it's a linear relationship. And it's almost a complete perfect linear relationship. It's not exact, but that would be a great model for this. Probably if we come up with a linear relationship, we then pick a number that we don't have here, like 5, 5 years, then, and we find some straight line through all of this. If we look at what 5 gives us along that line, it's probably going to be pretty accurate, because this looks like a pretty good data set as far as it's pretty predictable. So we should be able to do this, to come up with some kind of line on this, and that's what we're going to do. We're just basically going to figure out what line best fits this relationship. Okay, so what does that line look like? A straight line could be described as y equals mx plus b, where m is the slope of the line, b is where it crosses the y-axis. That's the y-intercept. What we are going to do in order to come up with the answer to this problem, problem description, we're going to try to find out what m and b are. Those are our variables in this this form, this y equals mx plus b. This isn't the only formula that the only graph you could do. We could do other types of regressions, not just linear. Like for instance, a quadratic description. Are you guys able to hear me okay? I just got noticed that somebody's not able to hear. Just want to make sure. Okay, so I got a positive from Vinod that, so yeah, got to figure out the logistics there. You'll be able to take a look at the video afterwards. Okay, oh, we got a question here. Okay, Katrina, you, great. Answered live, okay. All right, great, thank you, everybody. Okay, so yeah, there's quadratic equations that we could use here, more complicated, but we're just doing a linear regression to start with. So we're going to come up with this m and b. Those are our parameters we're going to try to find, with this linear regression model. All right, so here's another kind of picture of another data set. Here we drew a line, which is probably, pretty good fit, looks like it. And all of these are certain distance from that line, okay? And we call that E, that's the error, that every one of these is off. So what we're going to attempt to do is minimize that error. That's our goal. But this is actually what the formula would be for this, and each one of these would have a different error. Error E would be a vector, one for each of the data sets. So we're only coming up with a linear approximation of our reality. So, okay. So here we go. This is how we're going to come up with that M and B using matrix mathematics. So we started with this y equals mx plus b plus e. That's our formula for this this problem. So what we're going to try to do is m and b so that we minimize e. So we can rewrite this with using this mathematics. So y, if we consider y to be all of the y's of the data set, so all of this like 18, 5, 21, and then we rewrite mx plus b as x times a, where x is all the ones, a bunch of ones, one for every x that is, the going across. 1, 2, 3, 4, 5, 6, 7, 8. That's what all these values are, the x1 through xn. And we just put a bunch of ones, so this becomes an n by 2 matrix. N rows, 2 columns. Okay, and if we multiply that by this A, where A is B and M, where B is the y-intercept and M is the slope, we end up with this XA. And then this E is all of the errors. Okay, so if we assume that all of the E's sum up to be 0, okay, we can we can rewrite this, we can solve this for A. And this is how you would do it using matrix mathematics. And I'm not going into the mathematics in order to do this. It's pretty complicated, but basically this is what you have to do. You take y, you multiply by this matrix transposed. That's so it matches up, and you can multiply it. And then you take x and you multiply by x transpose. And then you take the inverse of that. Multiply by what we had before, you can end up with A. So I know this is pretty like hand wavy. Sometimes my favorite thing to do in mathematics. But the proof for this is fairly complex, and I haven't found any explanation of it that I like at this point. Otherwise, I would have gone through it with you. But this is, this is what you get. This is how you can solve this equation right here for A. Just real quick, if you take a look, there's enough, negatives and everything. X to the -1, both of these are to the -1. Okay. I mean, I'm kind of just doing a it makes sense type of proof here. If we take this -1 and put it through everything, and then the x transpose to the -1 times the x transpose, that will equal the identity matrix, and we know that that times anything equals anything, equals 1. That leaves x to the -1 that's multiplied by y, which if we just take this and multiply both sides by x to the -1, we get A. Now this E over here it sums up to 0. You know, it's balanced. So on average, it goes away. So that's the best I can give as far as a proof for that. Okay. And I apologize if this is kind of hand wavy, but this is the formula we got to do. All right. So let's look at how to do exactly this math in Python. Actually, when we get A, what do we get? We get B and M as an answer, which is what we want. So so let's jump into. I'm going to paste this into the chat. Maybe. Okay, hold on a second. Get out of the presentation mode. And I'm going to copy this in the chat so that you guys can follow along. Please let me know if that doesn't work. Okay, and back to presenting. Okay, and also just real quick here, some additional reading where I got this this code actually, and the math. I got it from this article. I did a huge search and pulled out the best one I could get, and then just kind of really paraphrased it. Okay, so let's look at. Oh, wait. Somehow I jumped ahead here. This is the one. This is what I give you guys. No. Okay, I sent you guys the wrong one. So if you will, that one we are going to be going over soon, but this is the one we're going to go over now. Okay. Sorry about that. Okay, so let's look at the gradient descent, or the linear algebra calculation of this. Okay, so first of all, I'm going to do is pull in a bunch of libraries, and I'm going to do this all from scratch here. Everybody following along? Pulled out your Jupyter notebooks, and you jumped over to GitHub to pull this in, and you were able to run the first bit of code. I really hope you guys are able to do that during class. That's, you know, in the future, when you go to other classes or you go to seminars and they're presenting, you know, code, this is what they do. It's what everybody does. So, and it's best if you can follow along in class, because then when you leave class, you know you have that solution with you and you can take it with you. Even if you get their GitHub, if you don't run, if you don't actually run it yourself there in class, then you're stuck. Audio not good. Okay. For some people, the audio is not that great. Okay. If you look at Srinivas, if you go to my website, you know, deepersideoflearning.com, and go to lectures, you got everything. That'll have the videos and the lectures. Doesn't have the GitHub, but then once you open the lectures, you know, the slides, then you can get there. Okay, so we're in the first bit. Let's go and grab the second one. Okay, now what I'm going to do, I created my own little data set here. And I am going to just cut and paste it. My data set is an array. The input is 0.05, 0.18, 0.31, 0.42, and 0.5. The output is 0.12, 0.22, 0.35, 0.38, 0.49. So based on this input, a number between 0.5 and 0.05 and 0.5, I am predicting this other one, which is between 0.12 and 0.49. There's no real meaning here. Apologize. It's just, it's some random numbers that I kind of pulled in. Well, actually, it's not random, but it's some numbers I pulled in from one of these other articles. Okay, so what I'm doing, see, I can go ahead and just kind of show you what all these are. So let's first look what input is. Input is just that array. So now what is M? Okay, M is just 5. It's the shape of the input 0, so it's how long is this? It's five rows is what M gives you. And it's just a number. It's just one number. So then I am adding ones to my X. Okay, adding a 1 to the beginning of each X. And transposing it so that it's a vertical like this. Okay, and my Y is the second row, and it's vertical. So I'm just basically breaking up my M and X, I mean my X and Y, and then I'm defining an M and using that variable. Just kind of killing two birds with one stone. Okay, so the next thing, oh, I didn't graph it. On the next one, next time we will graph this to see what it looks like, but you'll see very soon what it actually looks like. Okay, so then the next, I got a question. Why assume that the sum of E is 0? The reason why we assume that, and I can go back to an earlier graph. If the sum of all of these errors is not 0, then this line isn't the best fit. That's the best I can give you. It's balanced. Basically, the E's up are balanced with the E's down. So if you add up all of them and they equal 0, then that is actually the best line. It's not necessarily true, but you can think of it that way. If it's E sometimes is like a squared error, and that's what you end up with 0, or minimize, I should say. But in this case, we're just adding it together. Okay, so back to here. Okay. All right, the next thing we're going to do is actually do this whole exciting formula, which we're taking the Y. Well, actually, let's just taking the inverse of X transpose dot X, or times X, and we're dotting that with X transpose, dotting that with Y, which is the formula that we had here. Okay, got a couple other questions. Okay, or one question, I should say. What is the shape? Y is the shape of X n comma 2. Okay. Okay. Let's go back. If we look at the definition here, and it's we added a 1 here so that the ones multiplied by the b, and that the x is multiplied by the m, so that we have y equals mx plus b. And remember, we have many rows of this data set, x and y. So we were using each row, so we have to, so y sub 1 equals m times x sub 1 plus b plus e sub 1. Those are vectors, these x and y and e, they're matrices. So so in order for me to define this as x times a, so we can do this math, I need to put a 1 in front, so the 1 times the b gives me the b, and then the x times an m gives me the mx. So I hope that. Okay, and Monique has a good answer here. We use ordinary least square estimates of coefficients in line with minimizes squared error. Okay, that's complicated statistical math, which I try to avoid, but I know it's very important, it's very needed. But I guess that's the reason why this E sums up to 0 when we do this. Okay. All right, so here's that long equation. We're using linear algebra dot inverse, and we're using a dot product, and calculating A. And then what we're doing is we're saying A sub 1 is M, and A sub 2 is B, and I'm converting them to scalars so that they are actually numbers as opposed to more vectors. So when I run this, I get a print statement. I get B equals this and M equals this, 0.7. So I got a slope of 0.7 and a y-intercept of 0.08. So that minimizes my error, and that's my A. That's my final answer for this. So let's see what this looks like if we plug it in. So I'm going to plot it. I'm going to create these functions. Actually, what this is, we end up with XX is an array of 0 to 0.5 because we're mimicking our line. And then YY here, that's our X going across, and then our Y going up is using our B plus M times X, our slope times X plus our B. So therefore, when we plot this, voila, here are our original points, our data points. This is 0.05 comma 0.1 something, 0.12, 0.18, blah, blah, blah. And that's the line that we got, that we calculated with slope M and B. So beautiful, right? And we just calculated what this M and B is, based on those 5 points. And we can do this with any number of points. And part of your homework will be do this with more inputs, not just one input. We just had X1 or X here. Let's say we have several inputs, X0 and X1. We won't get a line for this because this is just, this is 2 dimensions, 1 dimension input, 1 dimension output. So you can't really graph that as a line, but it'll be a plane if we have 2 inputs. All right. So moving right along, that was our solution here with linear algebra. And please, if you didn't get any of this, ask now or catch me later, ask questions. No questions are dumb questions here. I know you've heard that. All right, so we went through this gradient descent algorithm last time with neural networks, and there's another way to calculate our M and B. It isn't with just a calculation like we just did. It's using an iterative method, just like we did with neural networks, to come up with it. So let's say we have so many variables, so many inputs, not just 5 rows of data. Let's say we have thousands of rows of data. If you can imagine this X, so let's say N was 1,000, okay? We're going to end up with this huge inverse. Now, inverse is very computationally complex, intensive, okay? And also this multiplication is a lot of numbers multiplying. So it doesn't make so much sense to use this matrix solution if we have a very large data set. But we still want to use linear algebra. We still want to approximate this with a linear function sometimes. Oh, I just realized I'm back on here. I need to present again. Okay. Okay, I got some questions. No, don't have questions. Okay, so now this time we're going to use an approximation of m and b, the calculation of m and b. You know, just getting closer and closer to it, rather than just having the answer. And this much more models the way we think. And as we'll see at the very end, this is actually very similar to, well, this is like a one neuron neural network. So, so yeah, we're going to start exactly the same way. You know, our linear regression is y equals mx, and instead of b, this rendering of it uses c, and I just kind of cut and pasted these formulas rather than rewriting them myself. So it's y equals mx plus c, a little bit different. All right, so our error matrix, we're going to minimize that because that's what gradient descent is minimizing our error. And our error is, okay, we're just going to pick some random m and c, anything, and then we're going to come up with what our algorithm will give us for y if we run it through this with our inputs. And then we're going to subtract it with from what we should have gotten. Okay, that's our error. So our error, and we're going to do the squared error because we want to treat negatives and positives the same. So if we square it, then everything's a positive and we can add it up. We don't want our errors canceling out. So then add them all up, and then this, this divide by n gives us the average squared error or the mean squared error. Okay, and we're going to do this mean squared error thousands and thousands of times, so get used to it. It's the basis for which our models are good or bad, is whether they have good error, low error. That's what we're trying to minimize. Okay, so now we're going to start calculating how to do gradient descent. And so if we take our other output, our linear regression output, and plug it in, okay, and it's our calculated one based on what our current m and c are. So we just plug it in there. We have this formula. Okay, now last time we did some partial derivatives. This time we're going to do partial derivative. Now what we're going to do is see what partial derivative means is what is the contribution of the error from m, okay, because we're going to adjust m to get the lowest error. We're also going to do the same thing with c. We're going to adjust c to get the lowest error, but we'll start with m here. So we have to do the partial derivative with respect to m, and the way you do that is you take 2, you multiply it by the outside, bring it to the outside, and then you take the derivative of the inside, which is with respect to m, which gives you a minus x. So simplify this, and you still have this y hat in here, which is our estimated output. Plug it back in. You take the minus, bring it to the outside, take 2 to the outside, 2 over n, and then you end up with this formula. So this is our partial derivative with respect to m. Okay. So So make sure I minimize the chat. So I want to make sure no other questions. Okay. So now next thing, okay, continuing, we're going to now take the same formula and do a partial derivative with respect to c. That is much simpler, much simpler answer. We get this one. And I think I missed a step in here, but this is what you get when you take the partial derivative with respect to c. So now we have these two calculations, dm and dc. We're going to move toward the answer by multiplying by a learning rate, a small amount. We're going to inch toward our learning, our answer of lowest error by adjusting m a little bit, adjusting c a little bit in the direction of downward derivative. So, all right, got a couple questions. Why do we need to find gradient descent? Okay. Okay, we got to find gradient. The reason why we're going to do gradient descent rather than just solving for it using matrices, because if we have a lot of data, thousands and thousands of rows, we need to. It doesn't make sense to do this matrix multiplication and inversion. It'll be much quicker, less computing time to do gradient descent to get to our answer. This is nasty if it's 1,000 by 1,000 matrix. Think about how big that is. And then we have to take the inverse of that. And if you think this other formula is complex for 2 by 2, just wait till you see it for 1,000 by 1,000. Okay, it's just so much math. Gradient descent is much quicker. So that's the reason for that. I hope that was your question. If it's not, go ahead and ask it again. Okay, why hat is defined as, or why would it have a little hat on it? That is our estimated output based on our current M and C. We multiply it M by X, add the current C, that guess estimated, and our current guess of our output. That's what y hat is. And if we take that current guess, subtract it from, let's go back here, subtract it from the actual right guess, because we're training to be a certain level, we have our error of that particular M and X, M and C. And we do square it and add it all up, then we have our total error. Okay. All right, so here's our formulas. Next thing is, you guessed it, we're going to do this in code. Okay, so let's see. Let me just go here somewhere. Here. No. Just give me a second here, trying to find. No, not here. Yeah, here we go. Okay, so I'm going to go back to our workspace and can I clear this? Okay, I'm going to go ahead and just start over. So I'm going to close my workspace and delete it. I don't need that anymore. I'm going to create a new one. Okay. And start from scratch. I'll just leave it untitled. I don't really need to. Okay, so we're done with this one. I'm going to close it out. Okay, so let's, okay, this is going to be our gradient descent. Plus, gradient descent doesn't take near as much math as matrix math. So, take another question. Is the equation used in the matrix method gives the best line? Yes. That's, by definition, that in order for that E to be 0, the sum of E to be 0 and give us, be able to do that, it gives us the best line. There's only one line that gives us the best error, the minimum error. Good question. I love these questions you guys have. It's just awesome. Okay, so loading up the libraries I'm going to need. We need NumPy, and we need pandas. Probably don't need pandas, actually. Okay, so, all right, and I'm defining my input, my data a little bit differently, mainly because I pulled data from a different spot. And plus, I don't need to create that X with the ones, the bias term. So what I did was I just split X, out. Here's an array, and then Y is, the other column. Okay, so, all right, now here I'm going to do a scatter plot of the data before I draw the line through it. Just to do that, I should have done this in the other one. This should all be synchronized between the two, but didn't have time to do all that. Okay, so the next thing is to build the model. So here's the code for running gradient descent. So I first set M and C to 0. These are, when in the neural network, first thing I did was I randomized M and C, or not M and C, but the weights. And we're going to show shortly that these are actually the weights. Okay, and I'm going to use a learning rate of 0.1 because I think I tried different ones and that one ended up being the best. I'm going to run it 1,000 epochs. I'm going to run the whole data set through my learning rates, my gradient descent 1,000 times. Okay, and now I need to know how many elements in X. So I just calculated that, the length of X. Calculated that N in the error, E equals 1 to N. I mean, summation 1 to N. So how many rows do I have? Okay, so I'm going to make a for loop through the epochs, and I'm going to run feed forward through my prediction here. MX plus C. So I take C, plug it in, M, whatever it currently is, initially it's 0, multiply by X, that gives me my first prediction. Then, okay, so basically what I'm doing here is I'm plugging in this formula. So go down, oops, where are we here? Okay, this formula, this M minus L times D sub M. So D sub M is minus 2 over N, blah, blah, blah. You look here, minus 2 over N times sum of X times X prediction. Y minus Y prediction. So I just reproduced that those formulas here for D sub M and C. But I needed Y prediction because that's my Y hat. Okay, name something different. Then I'm going to incrementally update M and C based on my learning rate, which was up here 0.1, and my derivatives, my partial derivatives. Okay, I'm going to do it for 1,000 times, and I'm going to print what I get at the end. Run it. I got 0.78 and 0.083. That probably should ring a bell. I already closed it, but you know what? I can open it again. Let's see how close that is to what we got. So 0.082, 0.0787, 0.078, 0.781, and 0.083. Okay, so it's okay. It's not as close to my actual one. So let's do an experiment here. I'm going to increase my epochs to 10,000. See if I get a closer answer. Now I got 0.787, 0.082. Wow. That's exactly what I got when I did the matrix math. It's, you know, it converges to that. So it works. Gradient descent is a way without that matrix multiplication to come up with the same answer. It's amazing. Love it when it works. Okay, so now that we have an answer, let's plot it. I don't want to use that plot. I want to use this one. So here's my formula, or my code for doing a plot. I create the formula here, and then I scatter plot. You know, basically, you know, I'm creating a straight line based on one end and the other end. So it's a fancy, you know, trick way of doing a formula here. I mean, a straight line. And you can see it's the best. It looks like a pretty good fit. So beautiful. Love it when it works. Okay, so I'm going to close that. Use site. Oh, yeah, I don't want it. Okay, it hadn't saved it yet. It does a periodic save every few seconds. Okay, so I'm going to close these things, all my code, go back to my talk. Okay. So, and the source of this comes from here. So, all right. So something that's pretty interesting about what we just did. This is from last week. A neural network, a neuron, I should say. It is a network, but it's a network of just one neuron with a bunch of inputs. So this is exactly what we looked at last week. So we have x1 through m, bias of 1, and then all these weights. And our formula, you know, we said we could pick any activation function, right? If we pick a linear activation function, which you can see sort of down here in the bottom, I could move this. Oh, there we go. That didn't move it. Still this. Okay, well, if I don't move, then you can see it. We picked a particular activation function. You know, I cut and pasted from the other, from the slides from last week. You know, the very first one that I showed was this identity activation function where, you know, I don't do a softmax, I don't do, you know, any squashing. I just pass through the to the output exactly what I had as a summation, as a weighted sum. So we end up with y equals y0 times the bias, and w1 times x1. If you take a look at this closely, you'll see that this is actually y equals mx plus b. We've got a bias here. The bias, if we set bias 1, then the b is actually w0. M is, depending on how many inputs we have to how many slopes we need. We only did one slope. So if we have multiple slopes, then, or multiple inputs, we need multiple slopes, just like we need multiple matrices, or multiple weights. So this linear regression is nothing more than a neural network of one neuron. If we have multiple outputs, not just predicting one output, predicting one value, if we predict multiple values, then we'll have multiple neurons. But it's only one layer. That's the key thing. Key difference between neural networks and linear regression is if we took all neural networks and only did one layer, not two layers, where this output feeds the input in another one, then we would not be doing anything other than linear regression. And if we change this activation function, we would be doing the classification form of it. So, all right, so that's basically it. Okay, I said apply to the iris data set. And I'd like to see somebody do that. The iris data set is a classification algorithm. I'd like to see somebody apply this linear regression to the iris data set. That's kind of a trick, sort of. But yeah, this is what I want to see for homework. The code for what I did was different between the two code sets, the matrix multiplication and the linear regression. So if you can make those similar, make them analogous, exactly analogous. I'd love to see somebody do that. Something else that would be good homework. Okay, compare the errors between these two. I want to see somebody do that. Give an idea of which one's got the better answer. We know which one's got the better answer, but I want to see that in numbers. Okay, then for just the gradient descent, I want to see somebody graph, or everybody graph the learning curve. That's really easy. We did that last week with the iris, the neural network, the graph learning curve. And also I want to see what the learning curve looks like with different hyperparameters. Are we getting better or worse accuracy with different learning rates? Because that's the only hyperparameter of this basic linear regression that we did. There's other tricks we can add to linear regression that we will. But right off the bat, learning rate was the only one that we talked about. Okay, then apply to the iris data set. Apply to a different data set. That's another application, another homework assignment. And I will just change that here. Iris or other data set. And when you go out there, you'll pull up the latest version of this when I post it. Okay, and then another homework assignment is modularize, which this is also homework from last week. Modularize this learning. Create a fit function that we just, it's a part of the linear regression class. It's a method. So fit, that will do the learning. And then we can put inside that fit two different learning algorithms. We can put the actual calculation of the answer or linear regression. I'm sorry, or gradient descent. Ooh, I know a good one here. I want somebody to, on a huge one, on a huge one, calculate the how long it takes to run. How long for large data sets. And I want somebody to show me that gradient descent gives you a good enough, reasonable answer without taking forever, taking a very long time. Okay, and then part of this modularization is creating a class, linear regression. Call it DSOL, deeper sided learning, linear regression. And then add hyperparameters to that, so we can set hyperparameters when we create it, when we instantiate it. And also add train and test split to this, but with another data set. So that's it. We actually finished a minute early this time. Let's see, any questions, any comments? Usually we go over, but linear regression is pretty straightforward. So next time I will go over the rest of the homework. Any additional homework I get, we will go over it. So you guys can get a feel for what everybody else is coming up with. And we'll kind of take it from there. So I guess if that's it, any other questions? Oh, okay. Yeah, I hope you guys enjoyed it. Again, I'll be around for like 10 minutes. I'm gonna go ahead and pop off the video and the sound. Yeah, throw me any questions. And just give me some feedback. Let me know how this all went, whether you found it very valuable, and also yeah, just send any of that kind of stuff my way. At some point, I'm going to start asking for stuff I can put on my website, for feedback, because I love doing this and I want to continue. And the best way I can do that is to have my students say good things. So, all right. Without further ado, I bid you a good evening. And again, I'll be around for about 10 minutes. Cheers.